Hey guys, welcome to the second video in the video lecture series on digital signal processing. In this video, we are going to go over a few applications of DSP and get more insights on discrete Fourier transform. You would also see a technique which can help us perform DFT quickly. Digital signal processing has a wide range of applications from the fields of communication to pattern recognition. Let's go over a few of them with the help of examples. Digital communication has taken the world to a completely different level. This diagram here shows the different paths involved in a digital cellular phone. Digital communication is preferred over analog even though the signal and medium are analog in nature because any signal can be represented as a digital signal with desired accuracy and can be reconstructed back with minimal error. This aspect helps us to reduce the redundancy in signal and also helps in data compression and the amount of data being transferred. There are two aspects again to this. They are source coding and channel coding. Source coding involves mapping of analog signal to a digital signal like converting speech, image into electronic form, whereas channel coding involves improving the accuracy of transmitted data by inducing redundancy such as transmitting a byte multiple times. Here we see that the natural signal, the analog signal, is taken as an input from the microphone, which is amplified and filtered, and using the ADC, it is converted into the digital domain. And after the required processing is done, it is again converted to analog using a DAC and is given out as an output. Another application is space-time array processing. This is a signal processing technique which aids in target or source detection of the signal. Here in this example, we see a NAV robot made by Aldebaran Robotics. This robot has multiple micro receivers on it, on the front, on the left, on the right, and on the back side. So when a person speaks, say, from a certain point near the robot, array processing is used to find out the direction from which the signal has originated. DSP is also useful in fields like information extraction, pattern recognition, etc. In this example, we can use DSP as a powerful tool to find the distance of the plane from the point in the airport. It can also be used to find the path of the plane, determine its trajectory, etc. Here if we see, the antenna receives the signal from the plane, which is then given as an input to the DSP system, which processes over the signal and gives out the output on the computer screen. Pattern recognition also has seen a huge growth with the inclusion of DSP. Areas like speech recognition, image recognition have seen a huge amount of research and development. In this example, we could try to find the note being played by an instrument. That is, we try to identify its fundamental frequency. We could also try to identify the instrument being used to generate the note. Like, different instruments have different patterns here. On similar lines, we could also use this to do speech recognition. We might want to distinguish different vocals like ah, sh, etc. So what we do is we take the speech signal, extract the required features we want, and feed it to our system, which then tries to identify the closest match to the given input vocal voice. Biomedical signal processing also makes use of DSP. One might not always want to reconstruct the signal back to the analog original form once when it's converted to its digital form. Here if we see, the biomedical sensor signal is used to check for any medical problems. Like we make use of ECG, EEG, etc. to find problems in heart and brain. These signals are processed and compared to that of a healthy person to check for abnormalities. Digital image processing also has a lot of applications. Like here, we can see it being used to recognize the number plate of a car from a given image. The different stages of output from the processing of the signal are shown here. One can use this as an application to generate fines for vehicles which are parked in no parking area and etc. Now let's move on to discrete Fourier transforms. DFT or discrete Fourier transform is used to find the spectrum of a discrete time-limited signal. It is being used in various fields like image processing, data compression, etc. The equations here, the analysis equation and the synthesis equations, are the ones which allow us to play around with signals in DFT. We can observe that it's computationally expensive to perform DFT using the above mentioned equations. The above mentioned equations can be represented using matrix operations in this way. So in order to calculate x0, we would have to multiply the first row with all the elements of the column here. To find x1, we would have to multiply all these elements in the second row with this column. So given n points in the DFT, the order for calculation of this would become O of n square. But there is a way to calculate DFT in a quick manner. The equations here, the periodicity equation and the complex conjugate symmetry equations, help us achieve that. Let's see how. So in order to perform FFT, we rearrange the DFT matrix in this way. In the column corresponding to the samples, we move the even samples to the top and the odd ones to the bottom. And in this matrix, we move the columns corresponding to the even samples to left and the ones corresponding to the odd samples to right. The sequence of the columns is same as that in the original matrix. This part here seems to be different. The entries here don't match to the ones in the original matrix. These are nothing but simplified terms of W48, W58, W68. So what we have done is we have computed the value of W48, which is equal to e power minus 2 pi j into 4 by 8, which is equal to e power minus pi j, which is minus 1. So the simplified values of these have been entered in the matrix here. If we observe, these values are just like the same ones but with a negative sign. So this overall matrix here can be represented like this in a short form, where W4 is made up of this 4x4 matrix here. These 4x4 elements can be represented as a diagonal matrix multiplied by W4, where this is W4 and this is the diagonal matrix. A special property of multiplication with diagonal matrix is that the entries of the diagonal only affect the row to which they correspond. So this gets multiplied only to the first row, this gets multiplied only to the second row, and so on. So the coefficients of the endpoint DFT here, xt and xb. Xt is the top part, the first 4 coefficients, and xb are the next 4 coefficients, can be found using these equations, where xe is wn by 2 small xe and xo is wn by 2 small xo. This is small xe and this is small xo. The even samples and the odd samples. So here if we see, we can compute an endpoint DFT as a linear combination of two n by 2 point DFTs. So now let's see the basic idea of FFT. Given an endpoint input sequence, we would divide them into two n by 2 point sequences, compute their DFTs and merge them to get the endpoint DFT coefficients. So we would keep splitting them from given n until we reach a point where we can't further split them, that is, we reach 1 point DFTs. So say if we start with 8 points, then we would split them to 4 each, and then we would take a 4-point sequence and further split them to 2 points each, and then we would take a 2-point sequence and then divide them to 1 point and 1 point. Now let's try to see the complexity of this fast Fourier transform algorithm. So given a n-point sequence, we would generally take the n to be of form 2 power b here. We would split them to n by 2 points and n by 2 points, one consisting of the even points and one consisting of the odd points. So we have seen that to calculate a n-point DFT using the normal equation simplification, the complexity would be n square. And to do the same using a n by 2 point DFT would result in an order of n by 2 whole square. So let's see what happens if we just split an n-point sequence to two n by 2 point sequences. The computation for a n by 2 point DFT would be of the order n by 2 whole square. The overall order that it would take to calculate the n-point DFT coefficients would be 2 times n by 2 whole square plus n by 2. These is for the two n by 2 point DFTs, and this is for the multiplications which we do for the odd part. If we further go down one more stage, that is, we split n by 2 sequences to 2 more n by 4 sequences, the order would become this. If we keep doing this until we reach 1 point DFT sequences, number of stages we would have undergone would be log n to base 2. Here, starting from 8, we would go log 8 to base 2, that is 3 stages to reach 1 point. Computation order to compute n-point DFT coefficients having split till m stages would be n squared by 2 power m plus n by 2 times m, where m is the number of stage in which we are. Having come down to 1 point DFT sequences, this term would become negligible, as the computation it would take to calculate 1 point DFTs is nothing. So the order of the algorithm would become n by 2 times m, and we have seen that m is log n to base 2. So the FFT's computational cost would effectively be of the order n log n. The equations of DFT can be modified slightly to represent the equations of fast Fourier transform. So what we do is we split the even and the odd terms here. The summation limit, which was initially from 0 to n minus 1, would become 0 to n by 2 minus 1. Let g of k be the n by 2 point DFT of the even terms, and h of k represent the n by 2 point DFT of the odd terms. Using the property omega 2kn subscript capital N is equal to omega kn to subscript capital N by 2. This can be shown by simplifying omega 2kn to subscript capital N, which is equal to e power minus 2 pi j into 2kn by capital N. The 2 in the denominator can be brought down, which would become e power minus 2 pi j into kn by capital N by 2. This term can be further split as omega 2kn subscript capital N into omega k subscript capital N. So once if we split this in such a way, we see that this would be equal to g of k and this would be equal to h of k. And x of k, which is the n-point DFT coefficient, can be represented as a linear combination of coefficients of n by 2 point DFTs. Furthermore, we can save on some extra multiplications which are being done here in this term. by using the periodicity conjugate property, which states that omega k plus capital N by 2 subscript n is equal to minus omega k capital N. So what we are doing here is the first n by 2 endpoint DFT coefficients are calculated using the normal formula, whereas the next set of n by 2 coefficients are calculated by just replacing this minus sign. This term we have already calculated before, so we would say another n by 2 multiplications here. So the first n by 2 DFT coefficients are found using this formula and using the same matrix here, and just changing the sign from plus to minus, you can calculate the next n by 2 DFT coefficients. This matrix here, the W matrix, is called as the twiddle factor. This W here is the twiddle factor, which is multiplied with the odd part of the n by 2 DFT. G here is the n by 2 DFT of the even points, whereas H is the n by 2 DFT of the odd points. W is multiplied with H, and a linear combination of G and H gives us the coefficients of n point DFT. That is, the n by 2 point DFTs can be linearly combined to find the n point DFT's coefficients. Let's see using an example. So here, this matrix W is the twiddle factor for a 2-point DFT, whereas this is the twiddle factor for a 4-point DFT. Let's see how to calculate a 4-point DFT using the FFT. Given 4 points 5, 0, minus 3 and 4, we split the even terms and the odd terms. Then we do the 2-point DFT, which is a plus b and a minus b, 2 and 8, and same here, 0 plus 4, 0 minus 4. And then we multiply the odd part with the twiddle factor. The even part doesn't change, it remains the same, so we have 2, 8, 4 and 4j. So now what we do is we combine these two parts using the formula which was already stated earlier. So we add the first and third terms, 2 plus 4 is 6. We add the second and fourth terms, 8 plus 4j. We subtract first and third terms, 2 minus 4 is minus 2. And we subtract second and fourth terms, 8 minus 4j. This sort of merging is called as butterfly merging. Now let's take a bigger example. Let's take an 8-point DFT. So I'd give you 2 minutes to just think of how to solve this. If you're not able to do it, then I'll go over it. Okay then, so what we do is, first we separate the even and odd terms. The 8 points are split to 4 and 4, and then each 4 point is again split to 2 points. And then a 2-point DFT is found here and here. Same is done for the odd part, and then the twiddle factor is multiplied to the odd part. And then we get these 4. So we merge these two to get a 4-point DFT, just like we have seen in the previous example, 3 plus 5, 5 plus j, 3 minus 5, 5 minus j, and the same here. And then again we multiply the 4-point DFT's twiddle factor to the odd part here. We get this resulting vector, and then combination of these two vectors in the first terms here, these two, and these two give us the first 4. Subtracting these two, and these two give us the next 4 coefficients in this 8-point DFT series. This technique is also called decimation in time, as we are splitting the even and odd time indices. Thank you guys for watching the video.